Hello, thank you for joining us. Let's look at some introduction to some sequences and series. This happens to be module 2B day 1 for the students that are sitting this class. So the definition of a sequence is nothing more than an ordered list of terms, and they are separated by commas. An infinite sequence continues indefinitely. It is noted with an ellipsis, the three dots at the end. So if I see three dots at the end, I know that this is going to go on infinitely. A finite sequence has a specific number of terms. So I will have some term where I stop. To write the terms of a sequence, you'll start your index, right? You'll start essentially your counter at 1 unless it's otherwise indicated. So for example, the first three terms of a sequence defined by use of n is n over n squared plus 1. Well, I'll start with n equals 1, and that'll give me 1 over 2. If n is equal to 2, that'll give me 2 over 5. And if n is equal to 3, that'll give me 3 over 3 squared. So that'll be 3/10. So what are going to be the first 5 terms of the sequence given here in 1a? Now remember, separate each term with a comma. I can come and I can list my things out and I can say, hey, 2 times 1 plus 1. Say 2 times 2 plus 1, 2 times 3 plus 1, 2 times 4 plus 1, 2 times 5 plus 1. Oops, careful with where we're putting those parentheses. The parenthesis location does matter. And so I can get my information and list out my first terms. So it's going to be 3, 5, 7, 9, and lastly 11. All right, that those would be my first terms of my sequence. All right. If I'm doing this work without a calculator, that's the way that I would have to go and do it. If I have a calculator, one of the nice things for us is that this NumWorks calculator has the place it asks for sequences. And if I come over and look at my sequences, I can look to add a sequence. And this sequence is what we call a first order it's called an explicit sequence. So I just have a term given by some relationship, and this gives me 9, right? And I have 1/2. Let's make sure we get that done correctly. And I am raised to that counter power. And let's go ahead and come and display my values. If I display my values, I see that my first term is negative 0.5. My next term is negative 0.25. Then I have negative 0.125. Then negative 0.0625. And then lastly, I have negative 0.03125. That's if I was doing the work with a calculator. If this was non-calculator, I could remember that 2 to the first power is equal to 2, 2 to the second power is equal to 4, 2 to the third power is equal to 8, right? 2 to the fourth will be multiplying that by 2, 2 to the fifth, multiplying that by 2 as well. And so I could say, hey, this is actually just negative 1/2, negative 1/4, negative 1/8, negative 1/16, and lastly, negative 1/32. That if I was having to do this work without a calculator, I could still do that work. Continuing, all right, some of the problems are really straightforward. So if I wanted the first 5 terms and I'm looking at this sequence d sub n, well, that's going to be 2 over 1, 2 over 2, 2 over 3, all right, and finishing out with the last couple of terms that there are my first terms. It's important to recognize that if I were to have simplified each of these, I would still be correct, but it becomes much more difficult to see the pattern if I have simplified. And when we're working with these sequences and we're working with series, we're going to want to be sure that we're not simplifying unless we're asked so that I can spot the patterns. Okay, let's look at the next one. We have our -1 to the n over 2n minus 1. Remember that if I have a -1 to an odd power, it's going to be negative. But if I have a -1 to an even power, that's going to be positive, right? If I start my counter at 1, 2 times 1 minus 1, then I could go 2 times 2 minus 1, all the way to, if I want 5 terms, 2 times 5 minus 1. So what does that mean for me? My first terms of my sequence are going to be 1, 3, right? And it looks to be that I'm adding 2 each time. So 5, 7, and then 2 times 5 minus 1, 9. So there's my terms. Okay. So what if I need to write a formula? Well, if I need to write a formula, I'm going to look for patterns. All right, so I look to see what do I have in common. And I notice that this is going to be plus 3 each time for 2a. If I look at the pattern for 2b, I notice that I'm going to be times -1/2 or divide by -2 each time for 2b. So what would be my formula for this? I could say that my nth term is going to be 3 times n minus 1. Why 3? Well, repeated addition is just multiplication. And then my first term is 2, so I need 3 times 1 minus something to get me to 2, so 3 times n minus 1. If I want my 20th term, that's going to be 3 times 20 minus 1, and that is equal to 59. All right. If I check out the next piece, we have repeated multiplication, and so I could say use of n, my nth term. With repeated multiplication, I'm going to have my first term, right? Repeated multiplication that I have, -1/2, and I'm going to say up to the n minus 1 power. Why n minus 1? Well, if n is equal to 1, that would give me use of 1 is equal to 64, right, times -1/2 to the 0 power, which is 64 that I need it to be. So I have that power of n minus 1 initially, and then if I'm looking for use of 10 then is going to be 64 times -1/2 to the 9th power, which would give me -64 all over 512. That would be my 10th term in this sequence. Do I need to simplify it? No, I do not. How did I get 512? Well, I could either start at knowing that 2 to the 10th is 1024, or I could start at the other side and say I know that 2 to the 5th is 32, and so 2 to the 6th is going to be double that. 2 to the 7th, that's going to be double. All right, 2 to the 8th is going to be double that still, so 2 to the 8th is going to be 256, and that gives me 2 to the 9th is 512. So it doesn't matter which approach that I use, I should be able to get to my particular values. With the calculator, obviously, it would be much easier because I could just say, hey, 2 raised to the 9th power, that's 512. Okay? This sequence in 2a has a common difference. Because it has a common difference, we call it arithmetic. Okay? This sequence in 2b has a common ratio. Because it has a common ratio, we call it geometric. Right? That information we'll look at in more detail in future lessons. So sometimes when we're working, you got to look at patterns, and you have to look at patterns to figure out what the relationship is going to be. So let's consider this sequence, and we notice that if I go from 2 to 5, I add 3. Go from 5 to 10, I add 7. Go from 10 to 17, 5 to 10, I add 5, and 10 to 17, I add 7. So if I call those the first differences, my new sequence is going to be 3, 5, 7. right? And then that would go on and on. What do I notice about the new sequence? Well, what I should notice about the new sequence is that there is a common difference in the first differences, right? So I have this common difference in the first differences, and so that's useful for me to know that if I wanted to get the next three terms in my original sequence, I would add 9, then I would add 11, then I would add 13. Right? So 17 plus 9, that would be 26. 26 plus 11, that would be 37, right? And then 37 plus 13, that would be 50. Of course, if we had a calculator, that'd be much easier to do, right? It would say, hey, what's 17 plus 9? Right? Okay, there's 26. Then plus 11. Right? Oh, then plus 13. And I could have those next terms in my sequence. And just remember that if it is a sequence, separate with commas. What about the 20th term of the original sequence? So if I wanted that 20th term, how could I figure it out? Well, what's important is to recognize that if our first difference is not constant, but that second difference is, the relationship between the terms is based on n squared. So that means that I need to think about n squared when looking at these numbers. So I can then quickly determine that a sub n is going to be n squared plus 1. Right, because that would give me a sub 1 is equal to 2, a sub 2 is equal to 5, a sub 3 is equal to 9 plus 1, which would be 10, and so I can see that that pattern holds. So what would a sub 20 be? A sub 20 would be 401. Why? Because it's going to be 20 squared plus 1. Right? So I'm looking for those patterns to try to figure out. If you don't see a pattern in those first differences, look for a pattern in those second differences. Okay, so let's see to this next part. Consider this sequence given by, write a new sequence based on the first differences. So 3 to 10, that's going to be 7, 10 to 19, that's going to, or 29, that's going to be 19, right? Then to 66, if the numbers are getting this large, you might have access to a calculator, so we can say our first difference is 7, the next difference is 19, right? Then I have 66 minus 29, that gives me a difference of 37, and then I have 127 minus 66, that gives me a difference of 61, and so these are the first differences. All right, now let's look at the difference between each of these. All right, what's the difference between those? Well, 19 minus 7. 19 minus 7 is 12. 37 minus 19, that's 18. All right, 61 minus 37, that's going to be 24. So notice that these second differences, right, the second difference have a common difference of 6. So therefore, I'm going to be based on n cubed. So what would be a sub n? My first term, if I think about cube numbers, my first cubes are 1, 8, 27, 64, 125. Those are my first cubes. So I look for this pattern and I see, oh, that's going to be n cubed plus 2. So a sub 25 would be 125 cubed plus 2. A really big number. Let's go ahead and use our calculator to figure out 125 raised to the third power plus 2. All right, and so I say, oh, and not 125, it's just 25. So let's make that correction. Let's go ahead and clear. So 25, not squared, 25 raised to the third power plus 2. That gives me 15,627. So that would be my 25th term. So look for these common differences, look for these patterns if you don't see a pattern initially. Okay? Now, a series. A series is nothing more than a summation. Right? A series we can think of as a summation. So consider the infinite sequence, a sub 1, a sub 2, a sub 3, to a sub I, going on infinitely. If I talk about the sum of the first n terms, we call that a finite series, or the nth partial sum of the sequence, right? Where the nth partial sum is just this summation, and we can use this notation to represent that sum. Okay? The sum of all the terms of an infinite sequence is called an infinite series, right? So if I added up all the terms going on infinitely, and remember the three dots means to go on forever, then I could have the same summation, but that top part of the summation would be infinity. Okay, so how can I do that? Well, one thing we could ask is to expand the summation. And remember, a summation or a series is nothing more than adding things up. And so I could come in and say, hey, well, what would be my first term? I'd start my counter or my index. I'd start it with 1, and I'd have 4 times 1 plus 1, then 4 times 2 plus 1, then 4 times 3 plus 1, and finally 4 times 4 plus 1. So this is going to be a summation. So I would have 5 plus 9 plus 13 plus 17. Okay. What would be the sum then? Well, I could add all of those up and say 5 plus 9 plus 13 plus 17, and that gives me 44. So there's my expansion and my summation. Right? If I wanted to do for this next one, here is what I have. I have a summation. My counter starts at 2. So I'm going to start with a 2, then I'm going to have a 3, then I'll have a 4, then I'll have a 5, and I'm going to go from 2 to 5, which gives me 4 terms. So this is going to be the same thing as 2 plus 8, which would be 10. 2 plus 27, because remember we're doing things cubed here, so 3 cubed is 27. So 2 plus 27, that's 29. 2 plus 64, that's 66, and then 2 plus 125, that's going to be 127. And so if I add those up, 10 plus 29 plus 66 plus 127, make sure I have those written in there correctly, and that gives me a sum of 232. All right, and so there would be my expansion, and I would have my summation. These summations I can do in a different way as well. I can come to my toolbox, go down to calculus, right, and arrow down to my summation, and I can type those in. So if I have a summation from 2 to 5 of 2 plus my counter cubed, notice that it'll give me that summation of 232. But here I had to write the expansion first. And so since I already had the expansion, I didn't need to use this piece. If I wanted to look at 5a, could go once again, right, and pick up my summation, and I'm going to be going from 1 to 4, right, and this is a 4 times my counter plus 1, and notice that I get 44. So it's useful to be able to check your answers. But for something as short as this, saying 5 plus 9 plus 13 plus 17 might be a little bit faster. But we'll see in the next video that we will need to be able to make use of our summation if we're going to have an easier time with longer and with harder problems. All right. I appreciate you. Thank you very much. And please watch our next video.